Hello students, in previous sessions we have seen many sorting and searching algorithms, right? And in this session we will see two different types of tree search. Okay, how we can make a search of a node, particular node in a tree type of structure, right? Because till now we have seen how we can be done the search in array of elements in a given elements, right? But when we are representing the data in hierarchical order, okay, whether it can be tree or a cyclic tree, nothing but a graph, when we are representing those type of nodes or values or items, how we can do a search, because it is not linear, right? If it is linear, what are the prior algorithms we have discussed, that will be appropriate, like linear search or sequential search and binary search, and this will work out, or interpolation search. But whereas there is a hierarchical relationship among elements, so how we can make a successful search, how we can search a particular node or element. So there are two interesting and important searching algorithm. One is called breadth first search, another is depth first search. Okay, so we'll just to see how breadth first search will be successful, and of course depth first search. We'll start with a very simple example. So what is breadth first search? What it will do, just it starts at the root of the tree and examines all the nodes at same level, right? It examines it on the same level before it's going for to the next level. So it will complete a level, each and every level will be completed, it will traverse each and every element, then only it will come to the next level. Okay, so for example, this is the given elements. Okay, this is the given tree structure. Now I want to search the node n. So how the search will be traced? So we'll see using breadth first search. That is what we have discussed. It will cover each and every level, then only it will go for the next level, and it will start from the root, right? So I'm starting at the root level, and so I'm starting with checking whether a equal to n, because n is our search key. Whether a equal to n, no. So what it will do, it just finish the level 0 and it will come to the level 1. At level 1, what are all the elements? So left to right, it will do the searching. What is the next element? B. And it will go to the, because it won't come to the next level until unless it finishes the particular level. And C, it is not equal to n. Then it will come to the next level. D not equal to n, E not equal to n, and so on. It finishes this level and it will come to the next level, and it searches for each and every element, and this is our goal state, right? The node which we are searching. And so here we have found our node. So this is the simple search flow, how we can find a node in a tree structured. Or in a graph also, we will see in a graph also where and all it can be applicable, because in graph we can have directed graph or undirected graph or weighted graphs. So many components are there, types are there. And in depth first search, and what is the difference? In depth first search, also it starts at the root and continues down to a particular path, right? So what it is finishing one particular path till the child node. Okay, whereas in depth first, whereas in breadth first, it finishes each and every level, then it starts with the next level. Whereas in depth first, it finishes on complete path from starting node, root node to till down to a particular path till child node form, right? So it continues down a particular path, selecting a child node at the deepest level of the tree, right? So only when the search hits a dead end node, then it will do the backtrack, that is continuing the search from the last node which in encountered, whose child node have not been fully examined. Understood? So we'll see, it starts with element A, and what it will do, it will search for a complete path till the child node reached. Again, we'll consider the search node is n, whether A equal to n, no, whether B, no, D, no, I. And here we don't have any other node to proceed. It reaches the child node. So that time what it will do the backtrack. It will do the backtrack, means again it will visit its root node, check for any child node it is there, because it will completely finishes the one path. So j is also not equal to n. Again it will do the backtrack. Yes, right children are there. It will start with the root node and it start checking with each and every node. No matching. Again it will do the backtrack. It will go to the root node. Complete left path is done and it will come to the right side. It is checking whether c equal to n. No, and it is coming left side, because it will finish the complete path, then only it will go to the next path. It will finish the complete path, then only it will go to the next path. But in this path itself we are finding our the search element or goal state, goal node. Okay, see the same tree structure, same search element, search node. Using breadth first search, we need 14 comparison. Okay, 14 steps we need, whereas in same tree structure, using depth first search, we could have done in this in with this 11 steps. Okay, so these are little comparisons. Each Both DFS and breadth first search have applications of its own. So this is very simple example how the searching is done. Just I will list out what are all the applications of both breadth first search and depth first search. So if we consider breadth first search, so what it will do, breadth first, it will finish each and every level from left to right, then only it will come for the next level, right? Where in breadth first tree traversal, it is used to find the shortest path of minimum spanning tree. What is minimum spanning tree? That is very shortest path. That is the shortest path. Minimum spanning tree is nothing but a shortest path with least number of edges. Right? We try to find the path that is shortest path with least number of edges covered. Okay. To find this minimum spanning tree, yes, of course, we can use either depth first or breadth first traversal to find a spanning tree. Okay, and in networks, peer-to-peer networks, in that we are using breadth first search to find all neighbor nodes. Okay, because why it is used? Because we will finish up one level, then only it will come for the next level. So by using this in networks, in peer-to-peer networks, breadth first search is used to find all neighbor nodes. Okay, and breadth first search is also used for crawlers and search engines. You know that what is crawlers and search engine. So here also we are using breadth first. Okay, so what is the idea it is following? What it will do, it will start from the source page and it will follow all the links from source page and keep doing the same. Okay, so depth first traversal can also be used for crawlers, but the advantage of breadth first is what? Depth or levels of the build tree can be limited. Correct. So we can limit the what is the depth or what is the level we have to do this uh, changes, right? So that is the advantage of using breadth first here. Also in social networking websites also it is very much useful. How it can be used to find people within a given distance, for example k, from a person, right? So what it will do, it will try to search till k levels. That is the purpose, k levels it will do the search. And of course in GPS navigation, how in GPS navigation we can use, it is used to find all neighboring locations. Okay, neighboring locations. So of course it will finish the one level, then only it will come to the next level. So obviously it is very much useful to find the neighboring locations. Okay. And in broadcasting network also, because in networks, if you want to broadcast any packet, it follows breadth first search. Why? Because to reach all the nodes, right, it should broadcast to all the nodes. Okay. And very simple example, path finding. Yes, we have seen, but to find a path between any two vertices, we can use either breadth first or depth first traversal. Okay. And also breadth first traversal is used for to find all nodes within one connected component. In this, either we can use breadth first or depth first to find all the nodes reachable from a particular given node, right? These are the advantages of breadth first search. Same here in advantages of depth first also, the same like breadth first. It is used to find path finding. That is, path finding is what? It is used to find a path between two given vertices. It can be U and Z. It is find one path between any two vertices. There also we can use depth first search. And of course it is used to find a minimum spanning tree, because both are used to find a minimum spanning tree. Both are used to find a path between given two nodes, right? And of course in topological sorting we can use depth first, right? Usually mainly it is topological sorting where we are using, it is used for scheduling jobs, right, from the given dependencies among jobs. Okay, there we can use. And of course to find strongly connected components of, so how we can find the strongly connected, that is, if there is a path from each vertex in the graph to every other vertex, so obviously it is strongly connected. So these are the different applications of both depth first and breadth first search. It's a very important topic, breadth first and depth first search algorithms. In lab we have to implement this, so now we'll just cover up the theory components. Next, another very important topic is hashing, right? Very interesting and very important topic. What is hashing, right? So hashing mainly mainly used for searching purpose. We will see how it is very much effective in searching an element. Okay. And it is comparatively very different from other searching methodologies, okay, other searching algorithms. We'll see what is the key idea behind our hashing. So if you consider hashing, just consider any field in a record, any field or any element, any string, anything you can consider that can be called as a key, and that key should be converted through some fixed process to a numeric value, which is known as hash key. Okay, I'll just explain. See, for example, we'll consider x, that is, we'll consider x as key. It can be any value. For example, as now I will take 5. Okay, so this is key, and I have to do some process that is fixed process. It should be, why it is fixed process? Because that process should same for all the incoming elements. That is why it's called as fixed process. So that value going to be converted through some fixed process to a new numeric value that is called a hash key. Okay, that numeric value in the range of 0 to n minus 1, yes, it can be, where n is the maximum number of slots or buckets, that we will see with an example. Don't confuse now. So what till now we have discussed, this is our key. This key is going to be converted to some other, so this is key. So what I have done, I applied some process So I applied some process on X on the key and I have got new result. Some fixed process, some process I applied on X and I have got new value. This converted value is called hash key. Okay, and through which process I have converted from this key to hash key is called hash function. So these are the basic, this is function. Okay, these are the basic items. What are the items? Key is an input. Okay, the element which you are receiving, that is input, right? That key is going to be converted to an another form. That key is going to be converted to a, that key is going to convert to another form. Okay, that new resultant value is called hash key. Okay, and through which process we have converted from key to hash key, that is nothing but hash function, right? So these three terms are very important. Okay, next. So hash function is nothing but a fixed process, we told, right? Usually it can be any formula or it can be any calculation. Okay, nothing but a mathematical calculation, mathematical formula, mathematical function, right? So how we can choose a hash function, that fixed process, how it will be, right? So based on, it depends application. Okay? If we need strongly if we need strong tough conversion, so we can use any tough mathematical calculation, right? It depends on our application. So but generally, how to choose hash function? So usually they will I mean, decide hash function by hash key is the division method of hashing. What is the division method? That is usually the hash key equal to key modulo number of slots in the table. That is one new key is coming, and in my memory I have, for example, 1000 location. Just for simplification, we'll just consider array of elements. Okay, 1000 array of elements. We have 1000 array of elements. So one element is coming. So among the 1000 empty spaces, I can put that element anywhere in that array, right? So what is the general formula, that how we can convert to hash key? The incoming key modulo number of slots. For example, I'm receiving the value 5 modulo I'm having 1000 number of slots. So what will happen? The result will be the hash key, right? And also the hash function needs to distribute keys among the cells as evenly as possible. Okay, so that hash function should give the result where we have to utilize that hash table completely as evenly as possible. So it should not give the same answer for many keys. So what will happen? So obviously some collision will happen. We will see what is hash collision also. And of course, hash function has to be easy to compute. Again, it depends on application. It should be easy or tough. It depends on application. But these are some common methods where we will try to follow to find a hash function. So it should be easy to calculate, and that hash function should be distribute all the keys among all the cells of hash table as evenly as possible. And how we can choose hash function generally? Using division method. What is the division method? That formula can be the converted value, that is hash key, equal to the new receiving value, that is key modulo number of slots in the table. Okay. We'll see with one example. For example, in an array of elements, just we will, for easy purpose, we'll consider any one array. In array of elements, index, what is that? 0, 1, 2, 3, 4. Okay, just consider array of elements. Okay, this I initialized, so the values are going to come. Before that, I have to fix that fixed process, right? That is hash function I have to fix. Hash function equal to, what is the key modulo number of elements in the slots. How many number of elements we can occupy? 1 2 3 4 5 elements, right? Somewhere it got moved. So function, short form I will write, function is equal to key modulo number of slots. In our example, number of slots is 5. So function is equal to key modulo 5. So now I'm going to receive value one by one. Okay, what is the value I'm going to receive? Say for example, the value 1. Okay, so the key is 1. How I can convert to hash value? How I can convert to hash value? This key modulo 5. So 1 modulo 5, 1. So I'm going to put this key in a first position. Okay. Here I'm going to put that value. For example, I am receiving the value 7. So what I have to do is 7 modulo 5. So 7 modulo 5, what will happen? That is 2, right? So the value 7 I'm going to put in the second position, right? And for example, I'm receiving the value 24. So 24 modulo 5, what will happen? 24 modulo 5 is nothing but 4. So the value 24, the key 24 gave the hash key number 4. So this value 24 is going to be put in the fourth index. So like this, I have to map key to the particular hash key value in the given allocated memory space, right? This is how the hashing will happen. So next we'll see one important term, hash collision, because maybe different two keys give same hash key. So that time what will happen? Obviously collision will occur. That is, different keys will give same hash key. So you see, we'll see how it happened. Okay. For example, before that we'll just see this example. So I'm receiving key 36. So 36, before that we'll see what is the hash function. Hash function is key modulo maximum number of size. As per our example, what is the maximum number of size? 1 2 3 4 5 6 7 8. So key modulo 8. So what is the key? The value 36 I'm receiving. 36 modulo 8. What is the value? 4. So at the fourth position I have to put the 36. Notice the next value 18. 18 modulo 8. This is why we are telling it as a fixed process, because it is a fixed process. The process is fixed. It should be applicable for all the values. And 18 modulo 8, what is the value? Position 2. So the value 18 I should put in the position 2, right? And the next key is 72. 72 modulo 8, 0. So the value 72 I'm going to put in a 0th index. Fine. 43 modulo 8, this 43 I'm going to put in a 3rd index. And 6 modulo 8, obviously 6. Right? So likewise, whatever the key I am receiving, I am applying hash function to get the hash key. Like this we can map. So for example, how it will be helpful, you may ask. For example, one new element is coming. Okay, I'm going to search 18. I want to search 18, whether 18 is present or not. So what we will do in another searching methodologies, in linear search, if we consider one by one, we will do the searching. If binary search, if we consider, we have to do find lower value, higher value, mid value, and we have to check for lesser, greater. And interpolation search, yes, we have to apply calculation and we have to find the position, then we have to check, then else we have to change the variables, so many calculations. But here, no need of comparison at all. See here, I want to search 18. What I can do, I can apply same hash function for this value. How? 18 modulo 8. So what value I will get? 2. So I don't want to search anywhere. I don't want to search anywhere. Straight away I can go to the second position, right? So I will see whether my 18 is there or not. Yes, my value is there. Then very good. My value is found. I don't want to search anywhere else. I don't want to compare with anything else, right? So this is how the hashing searching time is constant. Okay, so irrespective of values or calculation, the number of maximum number of slots, so irrespective of anything, the searching time is constant, right? Because here we are not comparing against elements, we are just applying hash function and we are trying on index, and straight away I'm going to the check with the index value. That's all. If element is there, yes, present. If not, element is not there. So that is why hashing gives constant time searching. So constant time searching means how we will the order of complexity, how we will give order of 1, because straight away we are applying hash function and we are finding the position, and I'm just straight away I'm going to check that index, whether my value present in that index or not. Yes, it is present. It means my value is there. So I don't want to bother about what is 72, what is what, nothing. I don't want to bother about anything, right? Next, hash collision techniques. Okay. So in the same example, we will consider what is hash collision. For example, I am having this is how I mapped. Now one more value is going to come. Okay. For example, the value, the key is 80. I want to store 80 in this table. 80 is coming. So what is the next step? I will apply the hash function 80 modulo 8. So what is the hash key value? I will get 0. So I want to put this, 80 at the place of 0. Oh my god, what will happen? See, at the 0th index already element is present, so how I can put this new element over there? That is, in the list of array elements, both keys, the key 72, this key 80, both different keys giving same hash key, right? Two different keys giving same hash key. So what will happen? How I can put both 72 and 80 in one place? That is not possible, right? So obviously collision will happen. That is why it is called as hash collision. Okay, if it happen in real time, how we can resolve this problem? So what are the techniques we can use to resolve these problems? That we'll see. The first technique is chaining method. Okay, there are four different types of techniques are there. One by one we will see. One is chaining, linear prop, quadratic prop, double hashing. So one by one we'll see how these hash collision resolving techniques will be used to avoid the collision. First one is hashing with chaining. So using chaining method, how we can avoid this collision? So these keys we'll consider 36. This is my first key. What is the hash key? As usual, key modulo table size. Key is 36, modulo table size is 8. So what is the value? Value is 4. So at the fourth place, I have to put 36. See here what we have done. We are not straight away putting our values in array, right? We are not utilizing this array for keeping the values. Instead, what we are doing, we are maintaining one separate list in each and every place. Okay, so here we are not putting elements in the array. Instead, we are utilizing the space to maintain one separate chain. We will see what is the purpose of separate chain. So what will happen? 36. Okay, modulate 4. So at the fourth index, I have to store value 36. Right? So it is done. Next value is 18. 18 modulate is what? 2. So in the second index, I have to put my 18. Okay, it is also done. We will see how it happened. And 72. In 0th place, I have to do. In 0th place, I have to put 72. And next 43, I should put in 3rd place. Yes, it's done. And 6 at the 6th place. Yes, it's done. And 10, my next is 10. 10 modulate 2. I'm coming here, already 18 is there, right? How I can make? That is the purpose of chain. What I'm doing, I'm just making connection, making a link between these two nodes, because both are pointing same index, both the different keys are giving same hash key. So I want to make connection between these two, so I just making connection. So how it is possible? For example, this at node value is 100, this node value is 200. How I can make this 200? I have to put here, right? And this node value I'm pointing here. So obviously this complete connection make a link, right? Okay. So what is the next? This is also done. And 5 it should put in the 5th place. Yes, it is done. 15 model should put in the 7th place. That is also done. For example, the value 80 is coming. As I told, the value 80 is coming. So 80 modulate, what will happen? It will give the hash key 0. So pick up. That is, I have to put this 80 into the 0th position. So how would this happen? Because already value is there. But here we are maintaining a separate link. So I'm just pushing ahead to next node. This 72 will come here, because I'm just pushing on place up the new incoming 80 will pop up here. Likewise, we can use chaining concept to avoid collision issues, right? We would see the next concept, hashing with linear probe. Linear probe, it will search for next available slot. That is linear. If it is not there, then it will go for the next available slot. Linearly it will search. Okay, you will see. Okay, we have to add, already we have added 72, 18, 43, 36, 6 as per same key modulo table size. And next we have to add 10, 5, 15. We will see. I want to add 10. So 10 modulo total number of size is 8. What is the value? 2. So I'm checking already at the place of 2 values available. So what I will do, I will go for the next available slot. Next, whether it is available, no. Whether it is available, no. So whether next slot is available, yes. So I can put 10 in the next available slot. It is done. Next 5 modulate 5. So I want to put my 5 value here, but what happened? Already the element is fixed, element is already added here. So I'm checking for the, here the element is already added. What element we have added? The element 10 we have added, so it is not free. So I'm checking next available slot, not free. Next available slot, yes, it is free. So I'm putting the value 5 in this position. So what is the next value? 15 is receiving. So I'm applying hash function, I get the 7. So 7th position, 7th index, I should put that value 15. I'm just checking 7. It is also filled. So I'm checking for the next available slot. No. Next available slot. Yes. So I'm putting 15 here. So this is also done. Likewise, in linear probe, it will search for the, if collision happens, or it automatically will search for the next available slot. Next, hashing with quadratic probe. Very interesting. Quadratic probe. The same like linear probe. What we have done in linear probe, we have searched for next available slot. Here, we are spotting quadratic. It means square, right? So here we are moving I square spot where the collision happened. I is nothing but how many number of attempts to resolve the collision. So we'll see with an example. So what is hash function here? Key modulo 10, right? Because we have 10 maximum locations, right? So 89 I want to put. So 89 modulo 10, 9. So ninth place I have to put 89. And 18 modulo 10, 8th place I have put 18. Next is 49. 49 modulo 10, 9. So ninth place I have to put but what happened? 9 is already filled, correct? Already filled. So wait, these elements, imagine these elements we didn't fill till now. Only these two done. Okay, only these two we have done. Next 49. 49 modulo 10, 9. So ninth position I have to put 49. Oh god, the value is already filled. So as per linear probe, what we got done, we searched for the next available slot. So how many movement we have done to find the next available slot? One movement, right? From here, next available slot, one movement we have to do. Since it is quadratic, we are using one attempt I have to make to find the next available slot. Since it is quadratic, 1 square. So 1 square is nothing but again 1. So I'm putting the value in this place itself. That is one move I have to do. Next is what? This is done. Next is what? 58. 58 modulo 10, 8. So I'm checking 8th place. It is already filled. So what I have to do? I have to check for the next available slot. How many movement I have to do? 1, 2, it is also filled, 3. So to find the next available slot, I have to jump 3 places. Since it is quadratic probe, I have to find number of attempts is what? 3. I have to find 3 square. So 9 spot I have to travel. See, I supposed to be here, but now 9 spot I have to jump. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 58. Sorry. Now this is 10. Next is 16 and modulo 10. So what? 9 again. 69 supposed to come here, but it's already filled. So how many attempts I should make to find new space? 1, it's already filled. 2. So 2 attempts I have to do. Since it is quadratic probe, number of attempts square. So 4 spots I have to move. Where it's supposed to be? It's supposed to be here. So 4 spots I have to move. 1, 2, 3, 4. So 69 will come here. So this is all about how to resolve collision using quadratic probe. The next technique we'll see. Hashing with double hashing. What is hashing with double hashing? One hash function I'm applying, collision happened, so immediately I can apply another hash function. That's all. We are using two hash function, but it is what it time complexity all definitely high, right? Because we have to apply two hash functions, right? Resource utilization is high. We'll see with example. Total table size is 10. In first hash key, I'm just with the declare initializing with key modulo 10, and hash 2 key I'm just using 7 because mostly we'll use prime number here. Most of the time we'll use prime keys. Hash 2 can be 7 minus k modulo 7. Okay, we'll start. 89. Initially, we'll imagine none of the elements are filled. We'll imagine none of the elements are filled. Can be empty. So 89 modulo 10 ninth place. Okay. So ninth place I have to put 89. What is that? 18. 18 modulo 10, it should go to the place 8. 8. What is it? 49. 49 modulo 10 9. I am checking for the 9 collision because already there. So what I can do, I can immediately apply the second has function. What is second function? 7 minus 49 modulo 7. That is what we have to do. The value 7. 7 positions, 7 spots we have to move from 9. It's supposed to be here, but now using second has function, we found that 7 spots it should move. 1, 2, 3, 4, 5, 6, 7. I suppose. But then should come here. Next is what? 58. 58 modulate 8. So 58 should be supposed to come 8th place, but it's already filled. So again, I'm applying next next has function. From the time finding 5. That is 5 positions from 8. This is 8. 1, 2, 3, 4, 5. Right? Next is 69 modulo 10 9. It's supposed to become here, but now already filled. I'm applying next has function. 7 minus k modulo 7, value is 1. So 1 position from 9. 9 is here, 1 position. Right? So it's all about hashing and hash collision resolving techniques. So this session we have covered 2 different tree search methods. One is breadth first search, another one is depth first search. Also, one more searching technique called hashing we have seen. The important terms are key, hash function, and hash key, and how to resolve the hash collision. What is hash collision? When two different keys are giving same hash key, that is nothing hash collision. How we can avoid? There are many methods are available. One is chaining, next one is linear prop, and third one is quadratic prop. So chaining method, linear prop, quadratic prop, and with double hashing, we can resolve the hash collision issues. Thank you guys. Next session, we will see in another topic. Thank you everyone.